Go.
Hi, this is Group 6. We are doing the Optical Interactive Chessboard for Beginners. My name is Alec Barno. I'm in Photonics Science and Engineering major.
My name is Vinicius. I am in Electrical Engineering.
My name is Alejandro Felix. I'm a photonic and science engineer.
My name is Nikolai Coletta. I'm a computer engineer.
And I'm Cassidy Phillips. I'm an electrical engineer.
So we use these bases to house our illumination system. We 3D printed these bases. We have a battery holder on the side of these bases. They will hold 2 AAA batteries, each over 1.5 volt. There will be an IR LED inside these bases and a circuit that will power these. The circuit consists of a button, the battery, and a 56 ohm resistor. We chose an IR LED since it has the smallest turn-on voltage compared to other LEDs. Our LED would be 940 nanometers wavelength, and our turn-on voltage would be 1.28 volts and current of 47 nanoamps.
So after we receive the light from the illumination system in the bases of the pieces, then for the piece identification system, there are photodiodes in the bottom of underneath the board, under each square, to receive that infrared light that will detect what piece is what. So with these photodiodes, we are using a transimpedance amplifier circuit because the photodiodes receive the light and output it as a low current, and we need to boost it up to a usable voltage number. We're using a 100K resistor for the boost to get up to usable voltages between the range of 0 and 3.3 volts. The other part of the chess piece identification system is the filters in which we differentiate each of the different piece types. So to do that, we use various neutral density filters to decrease the intensity of the IR light coming out of the bases. We attached all of those on the bottom of the bases. We glued them up to the bottom of the bases. And for our key spec, we achieved 7 different voltages to distinguish the pieces, 1 for each different piece type, and the 7th one is to distinguish the other colored pawn. We did that because pawns can only move forward, so being able to distinguish between white pawns and black pawns moving across the board was important, so that if we didn't, there could be confusion as to how the pieces get identified. And then after the light is received by the photodiodes, they send out a voltage to the microcontroller, so the microcontroller can then operate.
So once we receive the signal from those photodiodes, that signal is then transported along all of these wires and selected with a multiplexer to go directly into the teensy microcontroller placed way in the back there. Along those 8 analog lines, we're able to read 1 row at a time, and I go between all 8 of the rows very quickly, so then we get values from all 64 squares just by switching between all of them. With that, calculated ranges, that is just from the ADC, which is converted from the voltage ranges that you would get from the intensity of light going through each of the pieces, create corresponding ranges to be able to select what each piece would represent. So, for example, about 500 to 900 on the ADC range would correlate to a black pawn. Once that information is then stored into the microcontroller, we're then able to take it to the next step of the process and actually be able to play chess with these pieces. So once the information is stored and a piece is lift or place, depending if it's a legal move or not, or if it's like the first move, it will display different information onto an LED array of 8x8. Through all of that, you would be able to place the next piece or just do further action while you're playing the game. LED array would respond in different regards to that, and it's all based on how all of this information is stored and then copied over into different copies of itself, so then it knows to always keep a stable legal version of the board while the user can make a bunch of changes by accident or just misdetections that could happen from the ADCs in like rare cases. And with all of that, we'll be able to just play the game of chess on it.
There you go.
So I was in charge of all the PCBs of this project. We have 2 different designs. We have the 4x4 LEDs, which ended up being combined to make the full 8x8 as shown here. So I have an extra 4x4, so you can see that each quadrant measures 1.75 inches, which is the size of our square of our chessboard. And then in the dead center of each of the squares is the footprint for the photodiode. So you can see here that all 64 squares have a photodiode, an LED, and then a resistor for the transimpedance amplifier. And to save on the amount of soldering, we decided to do a quad op amp, which features the ability to work with low voltages, since we are currently only working with a 5-volt voltage source. And then that will amplify the signal from the photodiode and send it over to a multiplexer, which is controlled by our MCU. And we have 8 multiplexers to read through all 64 squares, so each one is in charge of 8 squares at a time. And then it will read that value and give the user an output based on how the LEDs are lit up. To control all 64 LEDs, we have RGB LEDs, which means we have 3 columns for the red, blue, and green, and then their common cathode configuration, so they all share a common ground or cathode. And then to make sure they light up properly, we have this kind of honeycomb structure, which we can place right over. And then when we place the lid, it creates an environment for all the light to disperse and go straight through the top without losing any of it.
To power everything, we are using a battery pack of lithium-ion cells. Each cell is 3.6 volt nominal voltage and 2.5 ampere of nominal capacity. They are arranged in a way that allows us to create a pack that's nominal voltage of 7.2 volts and a capacity of 7.5 ampere, which creates a 54 watt-hour battery. To charge this battery, we initially went with USB-C. However, due to some implementation difficulties on the further stages of design, we ended up going for a normal common 9-volt power adapter, which will be plugged in on a jack such as this one within the box that will connect to the battery through a board like this one, which is a battery management system board. This not only serves as an interface to the battery that will protect the battery from certain damaging occurrences such as short circuits or any possible overcurrent or overvoltage occurrences. It will also keep each cell balanced while charging, which is important because each cell is may not be chemically identical, so they may have different charging times and lead to self-destruction of the battery through charging if they are not properly balanced. The battery all end up feeding into a voltage regulator, which in this case we are using a switching regulator because they are more efficient in power than a linear regulator. And these will feed a 5-volt line to our main board with the microcontroller and further into the system to feed the remaining of it.
Alright, so now let's move on to some demonstrations. First, let me place the top back onto our board. And here we have the display, which will be just an interface for the user to be able to switch between menus and play the game. To show what it would look like during a normal game, if I go to New Game, so here we have a typical chess timer. The game can begin just by tapping one side, and the timer will just decrease for the opponent. And once you're ready to move on to your next turn, you'll be able to switch between them. You can even pause the timer if needed, or just resign if you feel like you don't have a winning position. All right, here we are going to demonstrate a chessboard simulator of just it detecting on all of the ADCs with the photodiodes. So take a look here. Here's a little chessboard. It's currently empty, as you can see, and there are no pieces on it, which is true. There's no pieces on this board. So if we grab a piece, so let's say the white pawn, for example, and place it in a square, and turn it on, you'll see that on the board there is a lowercase p, which represents a white pawn. Now, this is not just dependent on just one square, of course, because there's photodiodes on every single square, so you can see how it switches over here. I make a change, like place this right here, it goes over here, and etc. It represents it. You know, there's a little bit of bugginess with one king thinks there's a king over here, but these are values that we can adjust per square, per piece by adjusting the filter values. So just a little more calibration needs to be done before the final demo. The thing we can show off is the LED array underneath each of the square correctly working. I wonder if you can see a little better if we turn off the lights for it. So you can see here, have a little screensaver type of thing, just flickering between a couple different lights with the LEDs, just showing off that they all function.